Hello, Mrs. Suggs here to video the second half of the 11 video. I'll call this video number 11B. In this video, I am going to explain or show you how to address sample problems 3 and 4 in your pink packet. Example problems 3 and 4 are found on page 8 and 9. I'll share my screen and show you how I'm going to work in the pink packet to explain problems that combine both adding and subtracting, which is one rule, with multiplying and dividing, which is a different rule. Remember, there are two rules for propagating uncertainty. If you're adding and subtracting, you propagate uncertainty by adding the absolute uncertainties. If you're multiplying and dividing, you propagate uncertainty by adding the percent uncertainties. So what about a problem in which you both add and subtract and multiply and divide? That is a slightly more complex problem, but trust me, you'll get it, you'll practice it. This becomes an understandable topic for all students in IB chemistry. I'm going to share my screen and show you what I'm doing. So on page 7, is an example of propagating uncertainties with both an adding and subtracting component to the calculation and a multiplying and dividing component to the calculation. So I will show you here. You have an example of dealing with data. The data is A, B, and C, but the calculation you have to do with that data is to multiply and to subtract. I'm giving you examples here of what the data A, B, and C might be. You would have already decided in the laboratory what these absolute uncertainties are for each piece of data. So first we do the math. X overall equals just these numbers multiplied and subtracted. So do the math first and notice that this is the mathematical answer. You're only going to express it to 3 sig figs since some of the values only have 3 sig figs after subtracting. It might look like you have 4, well, here you don't have 4 sig figs, but nonetheless, you only write 3 sig figs in your answer. So now let's determine the overall uncertainty in the calculated result of X. You've got this parenthetical mathematics of B minus C. When you subtract, remember that you've got to add absolute uncertainties. So you add them to be 0.07. That is the absolute uncertainty of that parenthetical phrase. You've got the value A. For A, you're going to find the percent uncertainty because ultimately in A, you will multiply. But now you need to deal with the combined idea of B minus C. Since you'll eventually multiply the parenthetical idea of B minus C, you've got to take that absolute uncertainty and turn it into a percent uncertainty by dividing 0.07 by the value. So now you've got 2% uncertainties, one for A and one for this combined parenthetical phrase. You add the percent uncertainties together since you're multiplying, and your overall percent uncertainty is 1.2. Now, since that number is less than 2%, the overall percent uncertainty rule is I can keep 2 sig figs. Remember, I'll never grade you on this. So continuing on page 7. Now I've got my answer right here, and I've got my overall percent uncertainty. I have the 2 blue numbers up in the top. You might ask, how do I get the bottom gray numbers? You have to calculate that. You have to take 1.2% of your result. To take 1.2% of your result, you multiply it by 0.012. That's how you get your 10 centimeters as an overall absolute centimeters squared. That's how you get 10 centimeters squared as your overall absolute uncertainty. Plus and minus on each side of this visual, such that you can take your calculated answer and add the overall absolute uncertainty and subtract the overall the overall absolute uncertainty, and get the width of your error bar. Here I point out that the true value might be 1,057 centimeters squared. This true value would be outside the error bars, and that tells you something about analyzing your results. You would be able to either say that the true value is outside the error bars, or you could say that when you calculate the percent error, observed minus true divided by true times 100, you get a percent error that is larger than your overall percent uncertainty. That, of course, is the lesson for another day, but it does help you see why we're doing all of this propagation of uncertainty. So that was an example as demonstrated on one of the pages in your pink packet. Now I would like to look at example 3 with you. If you look at simple propagation of uncertainties, number 3, in your pink packet on page 8, here is the equation and the data that I'd like you to do. The data is to find D, E, and F with their uncertainties that you would have determined yourself in the lab. But the math that I want to do with this data is D plus E divided by F. Do you see that? Manipulation requires both the addition rule for propagating uncertainty and the dividing rule for propagating uncertainty. I am going to show you how to set up this page by slowly going over the answers. So I'm going to share my screen with my document visualizer. Here I have it. It will save me a little time and not make a 25-minute video if I work from this sheet. So my mathematical manipulation of my data requires me to both add and divide. That means this is a problem using both rules. This problem needs both rules, the addition rule and the divide rule. Make sure you're comfortable with knowing what those rules are. I emphasize that first, forget about propagation of uncertainty or propagation of error. You just do the math, write the equation, substitute in the numbers with units, and give me the answer to correct sig figs with units. Only after doing that do you propagate the uncertainties. Now let's look at this grid. I'm going to stop right here and talk to you about the pieces of data, D, E, and F. This is the insight that you need to acquire. Normally, this is not grayed out. You would have that as a decision you have to make. Look at D and E up here. You're adding them. Adding requires that you use absolute uncertainties. So when I write the data's D and E, I am very interested in the absolute uncertainties. Now, when I look at data F, I'm ultimately going to divide by it. So I want to take the absolute uncertainty and convert it into a percent uncertainty by taking the absolute uncertainty, dividing by this value, multiplying by 100, and there's my percent uncertainty for that particular piece of data. Now I've got two other mathematics that I need to consider. This parenthetical phrase here has a value. When I add D and E, it's 27.2. To talk about the absolute value of D plus E, I add those two absolute uncertainties together to get this. Now, since I am going to eventually divide the parentheses by F, I know I need to take the parentheses and also turn it into a percent uncertainty. I do that by taking the absolute uncertainty, dividing it by the value, multiplying it by 100. Since this percent is less than 2%, I'll hold on to 2 sig figs. Now, the last calculation, I have to ultimately take this value of D plus E, which has a percent uncertainty of 0.74, and divide it by F, which has a percent uncertainty of 3.3. I could have dropped that to 1 sig fig. It doesn't matter. Don't worry about sig figs. Let's just add them together, get this number of 4.0, and since that overall percent uncertainty is greater than 2, I'm going to drop it to 1 sig fig. The rule of thumb drops the overall percent uncertainty to 1 sig fig. So here, the answer is Y. Y has a numerical answer with units and an overall percent uncertainty of 4%. Now, how am I going to get this absolute overall uncertainty? Do you remember you do that by, down here, we would have gotten the 4% first. 4% of your calculated result gives you 0.07 for an overall absolute uncertainty. You add it, you subtract it, and get these exterior limits to your error bars. All of these values between 1.74 centimeters per second and 1.88 centimeters per second are acceptable and equally valid answers based on the data up here that you collected. Data that we acknowledge has a degree of uncertainty which propagates, that means grows larger, as you do calculations with it. So I hope by me showing you more about problem 3, you'll be able to do problem 4 on your own. Doing problem 4 would be a wonderful opportunity for you to practice what I have shown you. If you look at problem 4, once again, it is a combination of both adding, subtracting, multiplying, and dividing. You need to both multiply all those top numbers, which means you need to add their percent uncertainties. But you need to subtract the bottom numbers, which means you need to add their absolute uncertainties. Then you need to calculate the percent uncertainty of this parenthetical phrase so that you can add all of these percent uncertainties together. Remember, first you just do the math. Just give me a numerical answer and put it right here. You're going to first be calculating the overall percent uncertainties. That overall percent uncertainty needs to be converted to overall absolute uncertainties by another calculation that you do. It is by finding the overall absolute uncertainties that you can make these two extremes of your visual diagram of your error bars, acknowledging that not only your calculated answer using your exact data, but also this entire range represents the acceptable answers due to the uncertainties in every measurement that you made. I hope by looking at problem 3 and you doing a little bit more with problem 4, you might be willing to dip your toe into The homework of doing problems 5 and 6, both of which are combination problems. You have to use both rules to solve those overall uncertainty problems. You will get this day by day, step by step. Keep studying it, keep reviewing it. Every student masters this, and you'll get it by the test time next week. I thank you for your diligence. I have shown you sample problem 3 and 4. Actually, you'll have to be doing 4 on your own. I'll post this as video 11B. See you tomorrow in school.